The purpose of this lab is to observe the changing position of a slinky that is dropped from rest and to compare these observations with a computational model that predicts the position of the object. I analyzed the slinky's movement using Tracker and created a computational model that predicts its position using GlowScript. The computational model applies Newton's second law as well as the position update formula to predict the future position of the slinky. The fundamental principle applied in this lab is Newton's second law. Newton's second law relates the net interaction between system and surroundings to the observed motion of the system. To elaborate on this, Newton's second law states that an object with zero net interactions will maintain a constant velocity, and an object whose net interactions are non-zero will be accelerating. The velocity update formula, which I used in creating the computational model of the slinky's position, can be derived from Newton's second law. After writing in terms of final and initial momentum, I divided both sides of this equation by mass. Then, adding initial velocity to both sides results in the velocity update formula. The procedure for this lab was to analyze a video of a slinky falling from rest in Tracker, and from there, the procedure was to construct a computational model to predict and display the object's position. Here is a clip of the slinky falling that I analyzed in Tracker. The slinky is the system in the video, and I chose to orient the positive x-axis to the right and the positive y-axis is up. The origin is placed at the bottom of the slinky. For each frame of the video, which represents one time interval, I placed a pointer on the bottom of the slinky. I placed the pointer on the bottom of the graph so that the model I generated based on the video results would account for the bottom being stationary through the first couple seconds of the slinky falling. Doing this generated a graph of the slinky's position at each time interval. After tracing each change in position, I let the slinky's initial velocity be 0 since it is falling from rest. Here is a screenshot of the code for the computational model I created. First, I changed the object's mass to match that of the slinky, and I then updated the velocity and position equations to be the velocity and position update formulas. For the first while loop, the model predicts the unchanging position of the bottom of the slinky. With this being said, the net force was the weight force and tension from the slinky. I calculated the weight force by setting a new variable W equal to the mass of the slinky times acceleration due to gravity times the unit vector for the positive y-axis. The tension force is equal in magnitude and opposite in direction to the weight force because the position of the bottom of the slinky remains unchanged. As Newton's second law states, a system whose net interactions due to surroundings is 0 will maintain a constant velocity, and since the slinky starts falling from rest during the time interval from when it starts to 4.9 seconds, it will remain at rest and at the same position. Then I changed the time step delta t to match the time steps of the recorded data from Tracker. Lastly, I updated the initial position to match the position from the Tracker data. For the second while loop, I considered a drag force and weight force to be acting on the falling object. To add the drag force to the net force, I created 3 new variables, speed, v hat, and fd. These represent the magnitude, direction of the velocity vector, and drag force respectively. The drag force is the product of the square of speed, v hat, and the drag constant b. I found b by plugging in values until the final position predicted by the model matched the final position extracted from Tracker. The drag and weight forces are not exactly equal in magnitude during this time interval because the net force on the slinky is not precisely 0. Here's a graph comparing the data extracted from the observed and model position versus time graphs. You can see that the line representing the model diverges pretty consistently from the observed position. Sources of error that can explain the inconsistency between the model and observed positions are inaccuracies in tracking position in Tracker and other potential outside forces acting on the slinky. Another thing that contributes to this inconsistency is the fact that the drag constant was computed through trial and error, so the model overall is not exact. To conclude this lab, I'll talk about what affects the slinky's suspension in the air. The bottom of the slinky remains stationary because when the slinky begins falling, the net interactions on it are 0. For the first couple seconds, the weight force and tension in the spring are equal in magnitude and opposite in direction, so they cancel each other out perfectly. I would expect the bottom of a stiffer slinky to remain stationary for a shorter amount of time. My thought process behind this is that a stiffer slinky would behave more closely to a completely rigid object, and the behavior of a completely rigid object when falling is that the entire object falls simultaneously. I would expect the bottom of a longer slinky to remain suspended for a longer amount of time, since it would take longer for the top of the slinky to reach it and for the system to fall altogether. And that is all I have. Thank you.